If you want to teach an AI how gravity works, having it memorize a million photos of a dropping apple won't actually teach it the laws of physics.
Right. It just teaches the model what a falling apple looks like.
Exactly. And that is the fundamental problem with today's generative video models. So we are looking at a paper today called PhiZero, which introduces a massive leap for physical world models by utilizing a reason-then-render paradigm.
It's a completely different approach.
It really is. Because instead of generating future video frames directly in pixel space, PhiZero tokenizes a video into a discrete physical language using a transition-level Q-former and finite scalar quantization, or FSQ.
Which is a brilliant way to handle it.
Right. And then it uses a vision language model reasoner to predict the future state in this discrete language before rendering it all back into pixels via a diffusion decoder. The core insight here is that explicitly disentangling physical dynamics from visual appearance creates highly coherent, physically accurate world simulations that are honestly beating models like Sora 2.
Oh, absolutely. The benchmarks are wild.
So, welcome to AI Paperslop, where our mission today is to unpack exactly how PhiZero learns this physical language from unlabeled in the wild videos, and, why this architecture is a total game changer if you're working in physical AI or robotics.
Yeah, because to really appreciate why the authors built this architecture, we have to look at the catastrophic failure mode of current state-of-the-art video generation.
Okay, let's unpack this. What's the main issue?
Well, mainstream models attempt to predict future frames directly in high-dimensional pixel space, so the physics are left completely implicit.
Right.
Like a model like Sora or 2.2 might know that when a glass tips over, pixels representing water should eventually appear on the table, but the neural network itself has no underlying rigorous representation of gravity or collisions, or fluid dynamics for that matter.
It's just a highly advanced pattern matcher, right?
Yeah.
Operating on surface-level aesthetics.
Yeah.
Which is why we constantly see those bizarre physical hallucinations online. You'll generate a video and objects will morph through solid walls, or liquids will spontaneously flow upwards.
Or a character steps on a shadow as if it's a physical staircase.
Yes. Predicting physics directly in pixel space is basically like trying to learn the actual mathematical laws of classical mechanics by just memorizing a million flipbooks. You might get the general shape right, but you don't actually understand why the ball drops.
That's a great analogy. And the authors of PhiZero look directly at human cognition to solve this. Humans don't just memorize visual outcomes to navigate the world.
Right, we use language.
Exactly. We abstract our dense, continuous visual experiences into discrete concepts, into language, to explicitly reason about what happens next. The hypothesis here is that an AI needs an intermediate linguistic bottleneck to filter out the noise of visual appearance.
To just focus purely on the mechanics of state transitions. But, there is a huge caveat there. Natural human language has a severe granularity problem when it comes to physics.
Oh, definitely.
Like, if I prompt a model with "the honey spread across the toast," that sentence is functionally useless for a rigorous physics simulation. It doesn't give the model the viscous spreading rate or the surface tension.
Right, because natural language is far too coarse. It was built for human social interaction, not for calculating kinematic trajectories.
So they couldn't just use English?
No, they couldn't. They had to invent and learn a completely new, discrete physical language from scratch.
Wow.
They needed a vocabulary that captures microscopic state transition patterns across wildly diverse visual experiences. Everything from autonomous driving to a robot pouring water.
So if natural language is too clunky for physics, they are essentially forced to invent a brand new alphabet. How do you even begin to build a vocabulary for a language that doesn't exist yet, using just raw, unlabeled internet videos?
Well, this brings us to the physical language tokenizer. It requires a highly targeted architectural approach to separate the dynamics, the motion, from the appearance.
Right, because you have to strip away all the visual baggage.
Exactly. So they start the pipeline with a spatiotemporal encoder, which they initialized from the 2.2 VAE.
And if you're working with these models, a variational autoencoder, or VAE, is typically used to compress raw video pixels into a denser, continuous, latent representation.
But rather than extracting a global representation from the entire video clip, the researchers implemented a Q-former that looks specifically at the temporal interval between adjacent pairs of latent states.
Oh, I love the mechanics of this. Think of it like a motion-detecting security camera That camera doesn't care about the empty room, right? It only activates and records when a person walks in.
That's exactly what the Q-former is doing. It isn't looking at the static frame itself.
It's explicitly modeling the delta, throwing away the static room and only bottling up the change between state A and state B.
Yes, that delta is the secret ingredient. It uses a shared Q-former with 32 learnable queries to extract a transition representation for each temporal interval. But once you have that continuous representation of the motion, you have to discretize it to create an actual language of tokens.
And this is where they use finite scalar quantization, or FSQ. Let's break down FSQ for a second because it's a massive upgrade over how we used to build these vocabularies.
Huge upgrade.
Historically, if you were building a discrete latent space, you'd use a vector quantized VAE, which requires a heavy, separately learned codebook of vectors.
And those codebooks are notoriously unstable during training. You get index collapse where the model only uses a fraction of the available vocabulary.
Exactly. But FSQ sidesteps that entirely.
It really does. Instead of forcing the model to learn and update a complex dictionary of symbols, finite scalar quantization simply takes the continuous vector and rounds its values to the nearest fixed fraction on a predefined grid.
Which means it is computationally practically free.
Basically, yeah. For PHA0, they configured the FSQ with specific dimension levels 8, 5, 5, 5, 5, and 5.
So if you take the Cartesian product of those levels, meaning you calculate every possible combination across those dimensions, you mathematically generate a vocabulary of exactly 25,000 discrete symbols.
Without needing a separately learned codebook.
Okay, but I have to raise a major technical red flag here regarding the compression rate. They're taking a 33-frame high-definition video, compressing the temporal latent states down to 9, and then extracting 32 transition symbols for each adjacent pair.
Right.
If you do the math, the entire physical language sequence for a 4-second HD video is just 256 tokens. How on earth can a massive video be compressed into a tiny 256 token vocabulary without turning into a completely blurry, pixelated mess on the other end?
I mean, that brings us to the genius of the diffusion prior decoder.
Okay, tell me about the decoder.
So the decoder is a diffusion model initialized from WAN 2.2-5b. When they feed the physical language context into this decoder, they also feed it the first frame of the video as a clean visual condition.
So that first frame anchors all the static appearance data.
Exactly. The model already has perfect knowledge of what the room looks like, the color of the car, the exact texture of the asphalt.
Which means those 256 discrete tokens don't have to carry any visual baggage. They only need to encode the physics, the state changes.
They aren't wasting bandwidth trying to remember what a stop sign looks like.
That is wild. To put that in perspective for you, the baseline WAN 2.2 VAE requires 44,800 tokens to reconstruct that exact same 4-second video. PhiZero does it with 256.
And it actually achieves better reconstruction metrics, specifically PSNR and LPIPS.
And for those catching up on the acronyms, PSNR is peak signal-to-noise ratio, and LPIPS measures perceptual similarity. Essentially, this means the final reconstructed video actually has less distortion and looks significantly closer to human visual perception using a fraction of the data footprint.
It's an astonishing efficiency gain, really, because the diffusion prior handles all the heavy lifting of the appearance. But getting that decoder to actually listen to those 256 tokens required a very clever training intervention.
The pure noise warm-up trick. I found this part of the training methodology fascinating.
It's so smart, because when they first hooked this up, the pre-trained diffusion model basically wanted to ignore the new physical language tokens.
Right. It already had a massive pre-trained prior for denoising videos, so it just wanted to rely on its existing shortcuts to hallucinate the rest of the video based on that first frame.
Exactly. So the researchers implemented a pure noise warm-up. They took all the future frame latents and initialized them from absolute pure noise.
It's like taking away a student's cheat sheet. By initializing with pure noise, you are completely destroying the model's visual crutch.
It forces the model's hand. The diffusion decoder can no longer rely on structural hints in the latent space. It must pay attention to the discrete physical language tokens and the first frame to figure out what happens next.
And once the model learned to rely on the physical language, they restored the standard flow-matching noise schedule, and the representation quality just skyrocketed.
Yep. So if we step back, the model now has a 25,000-word vocabulary that perfectly describes past physical transitions.
We've solved the vocabulary problem. But if you want to build a world model, the immediate next hurdle is prediction. How does the model predict future transitions?
This is where they introduce the physical language reasoner. And because the vocabulary is discrete, just like text, they can use standard language model architectures.
So they initialize the reasoner from a pre-trained vision language model, right? Specifically Qwen3 VL4B.
Yes. And they extended its vocabulary by adding a distinct atomic symbol for each of those 25,000 FSQ indices.
So it's essentially treating the physics tokens just like new words in a foreign language.
Precisely. The reasoner takes that first visual frame, which represents the current world state along with a textual action intent, and then it autoregressively predicts the sequence of physical language tokens into the future, token by token.
Just like ChatGPT predicts the next word in a sentence. Here's where it gets really interesting, though. This raises a question that I'm sure every ML engineer listening is wondering.
The prompt enhancement question.
Yeah. Why did they need to build this custom language and fine-tune a heavy VLM on it? Why couldn't they just use prompt enhancement? We see this all the time, feed. A highly detailed AI-generated natural language prompt about the physics into the baseline video generator and let the pixel space model figure it out.
Well, the authors actually tested that exact hypothesis, and the ablation studies in Table 9 completely shut it down.
Shut it down how?
They took the WAN 2.25b baseline and used aggressive natural language prompt enhancement. That approach only achieved a score of 26.6 on the Physics IQ verified benchmark.
Ouch.
Yeah. But PhiZero's full physical language pipeline hit 41.2. Natural language simply lacks the mathematical granularity required for precise physical modeling. You really need a dedicated symbolic space to explicitly reason about mechanics.
And getting the model to understand those mechanics required a monumental hierarchical data curation pipeline. The sheer scale of the curriculum training here is staggering.
It is. They didn't just throw raw data at it.
Right. They started with a massive pool of 50,000 hours of internet video. Then they aggressively filtered that down to 10,000 hours of clean video for the tokenizer pre-training.
And that filtering process is incredibly rigorous. You have to strip out scene cuts, artificial transitions, and videos with low motion scores. I mean, if a video is just a static shot of a coffee mug, it teaches the model nothing about kinematic.
Right. It has to contain actual physical state transitions. From there, they refined it down to 5 million 4-second clips for the reasoner pre-training. And finally, they distilled that into a highly curated dataset of just 1 million clips for the final rich motion instruction tuning.
But we have to talk about the simulation data in that final 1 million clip data set. It wasn't just YouTube videos.
No, they heavily relied on curated simulator-generated samples.
Because the ablations proved that the simulation data was the missing puzzle piece for achieving high physical fidelity. Real-world video is messy, you know? Camera angles shift, lighting changes, motion blur obscures the action.
But simulation data provides pure mathematical ground truth for things like precise rigid body collisions, fluid dynamics, and cloth deformation.
Exactly. When the researchers removed the simulation data from the training mix, their IQ score dropped from 41.2 down to 37.7.
Wow. So the clean simulation data forces the model to anchor its physical language in actual physical laws, which it then generalizes to infer physically plausible transitions in the messy real-world videos.
Yes.
So the theory is brilliant, the FSQ architecture solves the tokenization bottleneck, and the data pipeline is immaculate. But how does this actually perform in the wild against the current titans of AI video generation?
It absolutely dominates across both generation and understanding benchmarks. On Physics IQ Verify, which measures the fidelity of physical outcomes, PhiZero decisively beats Sora 2, Cosmos 3, Grok Video, and Hunyuan Video.
It's a heavy-hitting list.
It really is. It also achieves the highest overall score in PhiGround, which evaluates adherence to physical laws. But honestly, the most revealing benchmarks are the likelihood preference tasks, like Causal and Causal.
Okay, the Causal benchmark is a fascinating way to evaluate a model's true understanding of the universe. In Causal, they test causal understanding by giving the model a pair of videos, one showing a natural physical event like a glass shattering, and one playing temporally in reverse, with the shards flying up to form a glass.
Right.
Because PhiZero explicitly predicts the mathematical likelihood of a physical language sequence, it doesn't just look for visual artifacts. It assigns a higher mathematical probability to the forward causally valid video than the reversed one. It can mathematically identify a causal violation.
It's so impressive. It also excels on LikePhys at identifying physically impossible fluid and rigid dynamics. It actually understands when a physical law is being broken, and you see this deep physical understanding most clearly in the qualitative examples they provided in Figure 4.
Oh, Figure 4 is wild. There's a comparison where a rotating stick swings and knocks a block off a platform.
Yeah, that one's great.
The baseline model, WAN 2.2, just animates the block sliding a bit and then glitching out. It completely fails to represent the downstream effects. PhiZero, on the other hand, doesn't just animate the initial impact. It correctly renders all the subsequent consequences.
You get the collision-induced displacement, the gravity-driven deformation as it hits the ground,
And a chain reaction with other objects. It even accurately renders the dynamically changing shadows on the wall as the objects move through space. The baseline pixel space models completely miss those secondary physical effects because they don't have a structured language for cause and effect.
And if you want to know why it can calculate cause and effect so well, you have to look at the latent space of the physical language itself. The researchers ran an emergent property experiment to see how these discrete tokens were organizing themselves.
Okay, tell me about that.
They took the physical language embeddings from two specific domains, autonomous driving and robotic manipulation.
And to visualize this, they ran PCA, or principal component analysis, to reduce the massive dimensionality of the data, and then projected it into a 3D space using UAP.
Right.
If you've never looked at a UAP projection, it's basically a way to take a complex, high-dimensional AI brain and squish it down into a 3D scatter plot that we humans can actually look at to see how the AI groups concepts together. And the visual clustering they got was absolutely mind-blowing.
Yeah, the physical language tokens didn't just group randomly. They naturally clustered according to real-world kinematic structures.
Which is incredible.
For the autonomous driving data, the tokens clustered perfectly into distinct, separate geometric manifolds for left turn, right turn, straight, and stationary. The model mathematically separated a left turn from a right turn in its brain.
And it was the same for the robotic arm. They formed completely separate spatial clusters for an action like sweep versus moving downward while closing the grip. The language didn't just learn a neat trick to compress video data, it organically learned the actual kinematic structure of the physical world.
And because the physical language is semantically structured this way and completely decoupled from the static visual appearance anchored in that first frame, it unlocks capabilities that standard video generators simply cannot achieve.
Like the zero-shot motion transfer protocol.
Exactly. That is the perfect example of this.
If you're building interactive media or robotics, this motion transfer capability is the holy grail. Because the physical language only encodes how things move, not what they look like, you can encode the physical language from a source video of, say, a human hand pouring a glass of red wine.
Right.
Then you use a standard image editor to change the first frame to a totally different environment. You could swap the human hand for a robotic gripper holding a beaker of green chemical in a laboratory.
And you just feed that new edited first frame along with the original physical language sequence extracted from the human hand into the diffusion decoder.
And the new object, the robotic gripper, will pour the liquid with identical physical timing, identical viscosity, and identical spatial trajectory as the human hand. The physics transfer perfectly without any additional training or fine-tuning.
It's incredible. And that modularity leads directly into its capability for action condition simulation. By feeding numerical text-like precise steering magnitudes for a car or specific joint coordinates for a robotic arm into the reasoner, the model translates those explicit instructions into exact physical language sequences.
So this creates a highly interactive simulator. You aren't just giving a vague prompt to generate a video of a car driving, you are feeding it steering angles frame by frame.
Right. The VLM reasoner is translating those numerical actions into the physical language tokens, and the diffusion decoder is rendering the consequential video based on the physics.
This allows for multi-step interactive rollouts, the camera viewpoint and the world state update sequentially based on specific control inputs you provide. So what does this all mean? When you synthesize all of this, the implications are massive.
They really are.
We are moving away from generative models that act like unconstrained hallucination engines. We are moving toward true interactive world models. These systems aren't just generating pretty fluid pixels. They are serving as rigorous, rules-based simulators for physical AI.
Because by treating physics as a discrete, translatable language, PhiZero proves that explicitly separating dynamics reasoning from pixel synthesis is the necessary path forward for the industry. Natural language is for human concepts and social intent.
But physical language is for the mechanics of the universe.
Exactly. When you give an AI the mathematically correct vocabulary, its ability to reason about complex state transitions becomes remarkably coherent and reliable.
Well, I want to leave you with a final thought to ponder as we wrap up today's deep dive. We just looked at how self-supervised learning on macro-level internet videos allowed a model to organically discover a discrete physical language for classical mechanics and everyday kinematics.
Yeah.
But what happens if we take this exact same FSQ architecture and train a tokenizer entirely on microscopic biological processes like cellular mitosis or complex protein folding? Or what if we train it on telescopic astrophysical data?
That's a wild thought.
Right? Could a future iteration of PhiZero learn and articulate a physical language for phenomena where we humans don't even fully understand the underlying rules yet? If we can find the discrete alphabet underneath the messy flipbook of our everyday world, maybe this architecture is the key to decoding the flipbooks we haven't even learned how to read yet. Thank you for joining us for this deep dive into the source material on AI paper slop. We will see you next time.